Hi, my name is Dhruv Kumar. I am a solutions engineer with the Global Alliances team at Hortonworks. And in this presentation, I will be explaining how you can use Internet of Things to bring value to the enterprise using Hortonworks Data Platform and Hortonworks Data Flow. The path we are taking to understanding IoT applications is as follows. We'll first look at a typical problem which an enterprise faces when they think of IoT applications. We're going to then look into how we go about designing the solution for that problem. Next, we will dive deeper into the solution design, and we will look at how many components do you need from HDP in order to build that application. We will also discuss the sizing of the individual components and machines needed to realize that solution. In the end, we will discuss briefly about the implementation plan and the project plan, how many people are needed for such types of projects, and we'll wrap things up by calculating the return on investment. So let's look at the problem which Ms. Brady, the CEO of Mega Corporation, is facing. Ms. Brady's Mega Corporation is a transportation company. She has a fleet of around 5,000 trucks, and the business, while is very good, can still get more profitable if they could save cost on insurance. So each of these trucks carries with them a cost of insurance premiums. And Ms. Brady wants to reduce the cost on that premium. Now, what she does, she hires a consultant, Tam, who is a business analyst, and she asks Tam to give her an estimate of how to cut cost and how much premium savings will they need in order to save, let's say, a few $1,000,000 per year. So Tam goes to her desk and she starts crunching numbers, and she comes back with this estimate. She says that in order to save $5 million annually, if they can just reduce a 10% incident rate on trucks, that will bring their trucks from a high risk to a low risk category, and they will be able to save a lot of money. So Tam makes this recommendation to Ms. Brady. So Ms. Brady is now aware of the situation. She has a goal in her mind. She says that, hey, I need to implement a technology or some way to reduce the number of incidents for each truck on an average per annum from by 10%, because that's going to reduce the premium cost of $3,500 per truck. And if you do the math, that becomes $5 million annually. So the focus over here, when Ms. Brady thinks about this problem deeper, is that one has to go from a very reactive approach to proactive. So rather than waiting for things to happen and the moving violations to occur or accidents to occur, Ms. Brady and her team needs to somehow predict things from happening as in advance. Then Tam also asks 4 questions. She considers 4 questions which might lead to the solution, which might lead to the final solution to reduce these incidents. The main questions are, is there a correlation of driver training to incidents? Meaning, if a driver has been trained well or for longer duration of hours, if they have received an advanced certificate in truck driving, for instance, do they become better drivers? The second question is whether if there is a relationship between the weather conditions on the road and the incidents. The other question is past driver behavior a predictor of future incidents? And the fourth question, it's like a meta question, is it possible to predict incidents before they occur? So while some of these questions might sound obvious, you still need to dig into the data to figure out if these correlations actually exist in this data set. So Tam poses these 4 questions to the team and Ms. Brady, and they get back to work. So Ms. Brady then arranges 3 more consultants, Varun, who is a developer architect consultant, Sue, who is a system administrator consultant, and Jeff, who is a data scientist consultant. And she arranges this team to have a go at these 4 problems, or 4 questions. But the team is a little concerned. The team says that, well, Ms. Brady, the data which you have given us, your existing data present in CRM and HRM solutions, and ERP solutions, those aren't enough for us to arrive at these conclusions. They say that we need to enrich this data by real-time event stream coming from trucks and also real-time events from weather stations, for instance. They say that we need to have more context around the data in real time in order to ask or even get closer to the solution to these problems. And they say that, well, some of the data we will need to arrive at this conclusion would be, first of all, we need vehicle data. We need to know how the truck driver is doing in real time. We also want to know what is the weather condition on the road where the truck is driving. We want to know the route data, for instance, if there has been any landslide on the route, so we can get this from National Transportation Services. We also would like to know what is the truck's health. How are the tires and the engines performing, and what has been done to the truck in the recent past in terms of its services, garage services. And we would also like to know more about the driver's, driving pattern from before. So basically, the team says that just the data which you have right now isn't going to be enough. We will need more and different types of data in order to solve this problem. So the team then also says that, look, your current architecture, which is kind of 2 or 3 decades old, isn't really suitable for us to even go and implement the solution. Why? It's because traditional data systems have been using the typical extract, transform, load type methodology, where different systems of record exist for different lines of businesses. And those systems of record are then transformed into a data set, which a data warehouse can use to analyze and crunch numbers on it. So the problem becomes that there are disparate data sources in different domains, in different application areas. And if you want to take a holistic view of the business, that is very, very difficult to do because of the problem of integration. How do you bring these data sets together, and how do you go about reconciling the knowledge present in each of those silos? So Megacorp is also facing with the same issue here. They have a very fancy enterprise data warehouse, and their data set about drivers and HR records and in fact service records for their truck are all spewed about in different types of silos. Secondly, the problem is the team says that even if we were able to somehow bring in more data into this data architecture and somehow reconcile it, this data architecture is not going to scale because all our new data sets, the weather data, the geolocation data, the sensor data, that's sort of semi-structured or sometimes even unstructured. And our current systems won't be able to handle it because there's no easy way to express the schema of those data sets into the current data warehouse. So one has to impose a schema right at the ingest time on the weather data or sensor data, and then bring them in order for any ETL to take place. So this is a very, very big stumbling block, and the current data architecture is going to limit them into achieving that solution. So they try to think of what can be done in order to modernize this data architecture. So they come to the conclusion that they will need a more modern approach to storing data and analyzing it. Then they realize that Hortonworks data platform and Hortonworks data flow, when used together, will give them the architecture what they need. In the next few slides, we'll go into the details of this architecture, but at a high level, what Megacorp did is that they used Hortonworks data flow to ingest all the real-time data from the trucks and also connect to the weather stations to enrich that event coming in. Then they stored that data into Hortonworks data platform, and Hortonworks data platform was then used to analyze all the data, build machine learning models, and build out that predictive app. Now, this is in stark contrast with the previous solution, where all the data was first landing into the disparate systems of records, and then ETL was done on it to bring it to a data warehouse, and then dashboards and visualizations were created. In this new architecture, we put data front and center. We say that we don't want to be designing applications around where data is sitting. We want to just take the vantage point of data, bring it all into a central place, and then move applications on it. Okay? So over here, HDP becomes the central place to store all the data in HDFS, and we will run some processes on it and try to arrive at the solution for Megacorp. Also keep in mind that HDP can also work and will work side by side with the existing data system. So we're not saying that Megacorp needs to throw out all their existing data warehouse infrastructure, all the machines which they have bought from the warehouse vendors, and the expensive software which is running on them. There are legacy processes which are running on these data warehouses. They can continue to run as is. HDP will be able to interact with them, will be able to query those data sets, and vice versa is true as well. The data warehouses can also interact with HDP, get data from it, look into what's data sitting over there, etc. So this becomes the blueprint and the template for a modern data architecture for Megacorp. So the team now understands that they have to modernize the data architecture, but they do have another problem. While these people are skilled in their respective domains, they don't know enough about Hortonworks Data Platform, Hadoop, Spark, Storm, and all the other pieces which will go into making that solution. So they also contact Hortonworks University in order to get trained on these concepts. So the team engages their favorite SI and attends Hortonworks University training to get the project underway. And if you go and look at Hortonworks training and Hortonworks University on our website, you'll find all these trainings available for these personas. So we have an HDP data analyst training, we have a developer training. Similarly, we have system admin training, which teaches just pure Linux system administrators on Hadoop administration. And then we also have data science training where people like Jeff can further take their knowledge from what they have learned about machine learning and apply it using Spark and tools available inside HDP. So now let's look at the solution design and customer case studies. We will now look at how did we go about designing Megacorp's solution and how you would do it if you were asked to do this for a typical customer. So solution architecture at a very high level, let's say 40,000 foot level, looks like this. Megacorp's trucks will now be fitted with some sensors which will monitor the health of the truck, its components' health. They will also measure how fast the truck is moving, how far away it is from the next vehicle on the road, etc. So they will give you real-time context about the truck. Secondly, we will also get weather data in real time. We will also query our existing SQL databases to understand the historical driving patterns of truck drivers. The SQL stores also contain the certification status of each driver and a lot of other info from legacy datasets. Lastly, the existing data warehouse machinery of Megacorp contains a wealth of information. They have been running queries which are cube type queries, and they give us a very nice insight into limited but nice insight into driving behavior and patterns. So we will also look into data warehouse and query information from it. So now we have 4 broad categories of data streams which we need to collect. We have truck sensors, weather data, SQL, and EDW. Now, real-time information like truck sensors and weather data will be collected by HDF. Okay? And SQL and EDW, which is more like a batch process, will talk directly to Hortonworks Data Platform. So HDF will be hooked up to truck sensors and weather data. It will ingest that data in real time and push it out into HDP. Now, inside HDP, over here you see there's a box here in the center which has Kafka, Storm, and Spark sitting. So that's where the real-time ingest stream lands in. These are stream processors which will operate on the data according to some predefined logic. And they will push out their results to Apache HBase, which is a fast, low-latency store. And they will also push out their results from HBase into a real-time web app. So the end product is a web app, which you see on the right side. this is the web app which our dashboard operator or the administrator inside Megacorp will be able to see. The idea is that with this real-time web app, the operator or the administrator in Megacorp sees in real time how the trucks are doing. So, so here's what the end solution looks like. Assume that you are the Megacorp's administrator or the driver health monitoring person. You'll be able to see on your web browser in a large display little dots moving around on these routes. Each dot represents a truck, and the color of the dot represents different status of the health of the truck and also whether a violation has occurred recently or not. For instance, over here we see that on this big green dot, if you click on it, you'll find that this driver's name is Jamie, and Jamie was going on a route from St. Louis to Chicago. This dot's radius is pretty big. The radius is directly proportional to the violation count. So we see that Jamie has had 60 counts so far, and the last violation which Jamie did was that he was tailing the truck in front of it or a car in front of it in a very unsafe manner. He was too close to the truck in front. So assume that you're the dashboard operator and you'd be able to see all these events in front of you. What can you do with this information? Well, because you have the records of each of the drivers, you can call them up, ask them how they're doing on the road, even advise them to take a break. You know, there are different things one can do to minimize the likelihood of this sort of a benign event causing major accident down the road in a few minutes. Okay, so Tam and Varun have built this application, and Megacorp likes it. You know, they are able to react to the things happening and you know, call the drivers in time and give them suggestions on what to do. But there is another thing we can do. Miss Brady is happy with these results, but she wants to push this even further. She asks Jeff, who's their data scientist, can we do better? So Jeff comes back with an answer. Jeff says that, like, look, Miss Brady, right now your administrators are just looking at these events in a very reactive manner. How about we predict whether Jamie is about to cause a violation or not in the next few minutes to hours? If we are able to predict events before they even happen, we can take a corrective measure and not be very, very reactive, and that will bring about even more cost savings. Okay? So Jeff then uses historical weather data and the driving patterns of drivers and comes up with a machine learning model, all using the tools inside Hortonworks data platform. And then the team uses that model to make decisions in real time as the events are coming in from the trucks, whether something bad is going to happen or not. And then they feed this insight out to the UI. So now the UI has been updated. The dashboard app has gone from version 1 to version 2, so to speak. Now, not only will the dashboard administrator or the operator see that Jamie is going from Des Moines to Chicago on Route 2, they also see that the weather conditions over there are, yeah, it is not foggy, but it is rainy. And they also see the certification status of the driver. And they also see how many violations this person is about to do in the next few minutes to hours. So we go from a very, very reactive to sort of proactive and prescriptive approach where we are able to predict violations from happening ahead of time. And we also can make recommendations to the dashboard administrator and operator what to do. So over here, the recommendation is to contact the driver immediately. So over here, the operator is obligated to call up Jamie and tell Jamie to take a break and, you know, start driving maybe after a night's sleep and so on. Okay. So Miss Brady is now happy. She says that, yes, I'm able to predict events before they occur, and this is a great, great thing for Megacorp's business, and they're able to reduce the insurance premiums, and they go down from a high risk to low risk category and save cost. Now, if you're wondering that this is a cooked up example, this is not. A similar project was implemented by Hortonworks with the city of St. Louis, where St. Louis fit the buses with sensors And we fed that information back into Hortonworks data platform to make similar analyses in order to improve road safety. I welcome you to go to this website link written here, hortonworks.com blog, St. Louis buses run with LHP telematics and Hortonworks. Please go to this link to read more about this study, because this will explain to you how we constructed this app, which I just described about Ms. Brady. So now we get into a slightly more deeper topic. We are going to peel the layer of the onion a little more, and now we're going to look at the reference architecture, the deeper architecture of this app, and the sizing issues for each of the components and the machine types involved. So at a very high level, whenever we talk about IoT applications in a big data context, there's a typical pattern we keep seeing in our implementations. So this is a very high level big data IoT architecture, which we often see. What this architecture entails is that for any new data stream coming in, there are two paths which the data stream takes once it lands into Hortonworks data platform or any big data system. One stream goes into one branch of the data stream goes into storage layer, where the information is persisted and archived in a rather slow, but a very, very high density storage layer. So this would be HDFS. So over here, the new data stream comes in, and one of the forks goes towards a storage layer, which is basically HDFS, and it's also called the batch layer. The other fork goes into a speed layer where we run some stream computation on it. Okay? So the batch layer, where we store the data for historical reasons, also runs some batch processes. For instance, you can think of these processes as machine learning processes, building models every few weeks to months. So these batch layer processes, what they do is they come up with pre-computed views. So you would have the data set here, you'll run some process on it and compute a view on it. Similarly, the speed layer, because it is processing the events and the streams as they're coming in real time, is also generating views, but these are incremental views. So these are not views which take into account all the previous history. They are very, very myopic, so to speak. They only look back at the information, let's say, a few seconds to a few minutes at a time, and they also generate their views. Now, we have two contexts here. We have the historical information views, but we also have real-time information view. Now, what we need to do then is when we are serving out our business app, we need to merge these two different views in a layer called serving layer. So serving layer is where you would design your web app and you would serve out the dashboards, etc. But the serving layer also connects to the batch layer and the speed layer and merges those two views together. This architecture is a blueprint for most of the IoT applications we see, and it's sort of taken from a fundamental view of big data applications by Nathan Mars, who coined the term Lambda architecture. So if you Google Lambda architecture, you can get more details on it. But this architecture looks very similar to the Lambda architecture produced by Nathan Mars. Now, if you were to take that same fundamental description of IoT and big data applications a little further, and let's put that into the context of our megacorp business. So in megacorp also, we were streaming data from the left side with different data sets. So we have server logs, application logs, sensors. You can have CRM and ERP data, which is basically driver information. Because the top of these boxes, for instance, sensor data and even server logs, these are all real-time data sources. We have to connect them to HDF in order to bring them into the Hortonworks data platform and the overall data center cluster. So this reference architecture will explain to you how all these components are fit together and orchestrate in order to arrive at the solution. So from the left side, we have all these data sets. Some of them talk to HDF because they are fast-moving data, but then CRM and ERP records, because those are SQL compliant data sets, we use a tool like Scoop in order to bring them into Hortonworks data platform. So again, at a very high level, HDF is useful for bringing in real-time data or anything which moves fast. So fast-moving data sets are connected to HDF to bring into HTTP, and batch type data sets are used, are brought into the cluster using Scoop. Okay? Once the stream has gotten into HDF, we then push out from HDF to a pub/sub messaging bus called Kafka. So Kafka is a component inside HTTP which allows you to integrate different systems with each other. It's a simple pub/sub messaging bus. It was designed by LinkedIn and they open sourced it, and HTTP now includes it in their distribution. It's extremely fast and scalable and reliable. You can set different levels of consistency guarantees on the messaging bus, and it's a completely open source solution present inside HTTP. So HDF to Kafka. Now Kafka will then do another thing. It will, going by the same principle here, we have the new data stream and we have to now split it into two different branches. Kafka will also split it into two different branches. One of the branches is going to go into this to the speed layer, which is where our stream processes are running. So this branch here, where it says forward to Storm, is our speed layer. And the other fork goes to the batch layer, or the layer where we store the data for historical insight. So the layer which is, the fork which is going to HDFS becomes your batch layer right here. And the fork which goes towards the real time or the speed layer becomes your stream processor layer. Okay? Now, once the event is stored in HDFS, we start doing some transformation on it. So because there are two different branches here, let me explain to you the lower branch. So the data set has now landed in HDFS. We now have to transform it because this data is just raw data. We don't impose any schema on it at ingest time. This is just binary blob data. We have to make sense of it. So how do you make sense of data in HDFS? Well, you can use tools like a Hive if the data is already in some sort of structure. For instance, if you have ingested this data and this data is in XML or JSON, you can easily use Hive with its JSON and XML SERDI implementations in order to convert it from the sort of semi-structured to a more structured form, so it is easier to analyze. That's our goal over here, broadly speaking. We have the raw data here. It might be in an unstructured to semi-structured form. We just want to transform it into something which is more useful for analysis, namely columnar regular format. Okay. We also can use Spark. So if your data set is extremely unstructured, it suffers from data quality issues, you want to remove certain records, do some analysis on the integrity of the data set, we can run Spark jobs on it. So Spark jobs will again look at the data in HDFS and transform it into something more regular, more useful, more cleaner. Okay. Once that's done, once that data set has transformed, it depends what you want to do with it. If you just want to do SQL-like analytics on it, if you just want to understand the historical information as it is sitting, you can just run either Hive SQL and connect your other reporting tools to Hive SQL via Hive server, or you can also run Spark SQL on it if you just are interested in question and answer type queries. But if you want to do some more advanced, what you could do is take that same data set after transforming from Spark, give it to Spark ML. Now Spark ML will then use the more sort of structured data and build out machine learning model on it. So you can now use Spark ML to build machine learning model, and then you can store that same model back into HDFS. And what you can also do is then can use that same model, which is present inside HDFS, into your stream processor. Okay. So now, so far we have just talked about the batch layer where we are running all these batch processes. The data set has come in, we have transformed it, and then we have either put a machine learning model on it, or we have just stored it in a structured format in Hive. But then the stream processing layer also is operating now, and it is using the same machine learning model which you have built using Spark, or it could also be running some simple process, some windowing calculation, for instance. Okay? So the bottom line is that batch processes and batch layer will be useful for historical insights, machine learning model building purposes, and the stream processor will use those types of insights and those type of models in its own real-time stream and apply them to events as they're flowing in, and and give us the prediction. Okay? Now, if you look at this diagram, there's also HBase sitting here. Why is that used? Well, if you go back to our architecture of the Megacorp's business and the solution we proposed, we said that the events are coming in from trucks, but we also need to get weather data, real-time weather data, in order to enrich the context. You see, we have the sensors on the trucks, but they are not telling us whether the road is foggy or not, or how much rain is falling on the route at that point. Okay, so we need to be able to get weather data and enrich the context of these events before we can apply them to our machine learning model. The machine learning model itself expects that you give it not only the real-time event data, but also the real-time weather data. Now, how will the stream processor over here get real-time weather data? Well, if the stream processor then starts making calls to a low latency, a store like HDFS, that's not going to cut it. So what Spark streaming and Storm streaming do is they need access to a very fast, low latency data store, which can give them simple information right down to the latency of, let's say, less than 20 to 30 milliseconds, so that they can keep up with the demands of the SLAs of any real-time dashboard. So for that purpose, we use all the lookup tables and the real-time event enrichment context data inside HBase. So HBase is another data storage which is present on HDFS, and it allows you to query real-time data in a very fast manner. Okay, so that becomes your fast query store, which you would use in order to enrich the event context and make some decisions in real time. Okay? So that becomes the broad detailed reference architecture for IoT applications. Now let's look at the components present in that architecture in a little bit detail. So the first thing is Apache NiFi. So NiFi is the guy sitting inside HDF. That's a project which is wrapped by Hortonworks Dataflow, which does the main work. So NiFi is a tool which came out of NSA, and it has been in existence since 2006, but it was open source, I think, in 2013. So NiFi allows you to connect to different data sources over the internet, and also, sitting on your machines. You can ingest log files, you can connect to Twitter data, you can connect to event sources, for instance, sensor data, you can listen on ports. It exposes a nice graphical user interface where you can drag and drop these processors and build out flows. You can look at data provenance events and so on and so forth. So over here, you would first use NiFi in order to build out what we called a flow topology, and that will allow you to connect to the sensor data coming out of the trucks, and we would put that into HDFS, or we would give it to Kafka. So over here, I show a put HDFS processor, but there's also a send to Kafka processor. So what you would do is you would drag a processor to listen on let's say, a specific port where the events are coming in. Then you would drag another processor here called store to Kafka, and that Kafka, and then you would configure both of these processes with certain properties. In the Kafka processor, you will tell it where the Kafka brokers are located, what's the topic, etc. And in the ingest processor, you would tell it what's the event size and what's the attributes, etc. Now, once it is inside now we have ingested the data using NiFi. We have given it out to Kafka processor. Now, Kafka, if you know, connects to Storm in our reference arc. So here we have brought the data into HDF, then Kafka. So this connection was done using NiFi and Kafka processors themselves. Now, Kafka needs to talk to Storm, which is our stream processor. You can also use Spark streaming, but we will use Storm for this example. So Storm is a true stream processor. It's another open source component present inside HTTP. By the way, all the components inside HTTP are open source. There is no closed source component. So Storm is a true stream processor, which was developed again by Nathan Mars. It's extremely scalable. It guarantees processing. It supports different types of semantics, at least once and exactly once. It is language agnostic. You can program Storm using any JVM language, really. It is an Apache project, so it has a governing body and a very large active community. Okay. Now, the basic concepts in Storm are that Storm operates on a notion of topology. So the flow which you describe in Storm is comprised of spouts and bolts. Spouts are the data generators and the bolts are data processors. So in our case, we will write a spout called Kafka spout, which will generate or which will transmit the events ingested using MiFi from to Kafka to Storm. So we will have a Kafka spout, for instance. And then let's give it, then we will, for instance, come up with a bolt called, machine learning, my machine learning model bolt. That bolt will have the logic from your side, from our side, which will operate on the events as they're coming in and make some predictive analysis. So this is the basic structure of a Storm flows. A Storm app is nothing but spouts and bolts connected with each other, stitched together either by using tools like Trident or using tools or just using the Storm API. Once you have the topology with you, the spouts and bolts connected with each other, you just give it to Storm process, Storm's super main process, Nimbus, which is the master node for all the Storm topologies. You give it to Nimbus node, and it will start executing it until infinity. Okay, so this process will keep running as long as you kill it. And the process basically just sits there waiting for an event to come in, and as soon as it comes in, it will start doing some calculation on it, analysis on it, described by your logic. Okay. The HBase component, which Storm and Spark Streaming typically use as a lookup table and also to store data during runtime. It's an extremely scalable distributed store sitting on top of HDFS. So HBase doesn't store any data by itself. It uses HDFS data and stores back on HDFS. It's got a dynamic schema, so the meaning that you can interpret the schema as you wish. And it uses, again, Yarn as the central layer on HTTP for its implementation. Apache Phoenix. So if the HBase API is get and put. It's HBase. You can think of HBase as a blob store. You can put a key with a value in it and get a key and value out. But if you would like to do something more concrete and more SQL-like, you can use Apache Phoenix, which is a SQL engine on top of HBase. It was released by Salesforce to the open source community a few years ago, and now it is a first-class citizen inside Hortonworks Data Platform. So you can use Apache Phoenix to connect to Apache HBase and query it as if it were a SQL store. Apache Phoenix also exposes a JDBC interface, so your reporting tools can connect to Apache Phoenix. Hence, in this architecture over here, when the events are persisted in HBase through Storm or Spark Streaming, you can use a dashboard like Silk to connect to HBase using Phoenix JDBC. Let's talk about Spark for a second now. So Spark in our reference arc, we used to transform the data, and also we use Spark for our machine learning purposes. So that's what Spark is usually used for. It has three components in it, actually four. There's a base Spark core API right at the bottom here, shown here, where it's the core engine, core API services. And on top of that, Spark comes with different modules. So there's an MLlib, which is the machine learning module. There's Spark Streaming, which allows you to do stream processing on data sets. And then there's also Spark SQL, which allows you to do SQL-like access to the data sitting inside Spark. So Spark is an extremely useful tool for building machine learning models. In fact, it's probably the only tool out there right now in the broad big data community which can build models at the scale of big data sets. So extremely large data sets, if you want to do iterative machine learning on it, Spark is your answer. It's distributed, it keeps most of its data in memory, hence it is very, very quick. Unlike batch processors like Hive, which try to use disk as their focal point. Again, Spark can be used via any JVM language. It is written in Scala, but you can also program in Java. You can also program it using Python using a tool called PySpark, which is bundled with Spark. So data scientists who are not very comfortable, let's say, with Scala or Java can still work with Spark using Python. In the recent versions of Spark just released, Spark also can be used using R. So there's a binding called RSpark, which allows you to run R code on Spark. So Spark ML, MLlib is the machine learning layer inside Spark. It has a few different algorithms commonly used by data scientists in big data community. It doesn't contain all the algorithms which are, for instance, prevalent in, let's say, Weka or some other tools or present inside R. The reason being, some of the algorithms cannot be broken down into embarrassingly distributed problems. Hence, Spark can't work with some of the other machine learning algorithms. But for the most part, the commonly seen big machine learning algorithms are implemented in Spark. So for instance, you have k-means clustering. We have a recommendation, ALS recommendation algorithm, using which you can build recommendation engines. There's dimensionality reductions for you to reduce the number of features from a highly dimensional data set, and so forth. So Apache Hive is the SQL layer of Hadoop. This is very well known. This is perhaps the most well known of all Hadoop components. It was created by a team at Facebook. It provides a standard SQL interface to data stored in Hadoop. And it's proven at petabyte scale. So Hive works really well at massive data sets. It can scale. It scales out very elegantly to petabytes and petabytes of data sizes. It's compatible with all major BI tools because Hive basically exposes an ODBC interface. So the major BI tools connect to Hive using that ODBC interface. So whatever you do on your BI tools in a GUI layer is pushed down into Hive for processing. So Hive is a very convenient tool if you're a SQL expert and you'd like to analyze the data sitting in Hadoop or using SQL-like language, you would use Hive for it. Okay. So we have now 3 options for SQL in HTTP. Let's compare them. So we have Apache Hive, we have Spark SQL, and we have Phoenix. So Hive's strength is that it has been proven. It's the oldest of these 3 tools. It's been proven at scale. It really shines on extremely large data sets. It has the most comprehensive SQL. It has the most comprehensive SQL compatibility out of all these 3 options. And the common use cases for Hive are typical ETL offload, large-scale aggregations. Spark SQL is a recent entrant to this field. It is because Spark uses memory aggressively and it keeps most of the data inside memory. It is extremely quick, so you would use Spark SQL for slightly smaller data sets. You would not use Spark SQL on petabytes and petabytes of data. For those analyses, Hive is your best option. But for small to moderately sized data sets, most of which are present in the memory of the nodes, you can use Spark SQL. Apache Phoenix is a SQL interface to HBase, and it is really just a more convenient way to get to data of HBase. If you are not familiar with the HBase API, you could just use Phoenix in place of the API. But for real, true processing, SQL-like analytics processing, you would use either Hive or Spark SQL. Okay. Also, keep in mind that there are 2 stream processors now in HTTP. One is Storm, and the other is Spark Streaming. What is the difference between these 2? Well, Storm is a true stream processor in the sense that it can do event-by-event stream processing. It will apply the logic you define in the topology to each event as it comes in. Whereas Spark Streaming can't do event-by-event. When you have the data coming inside Spark Streaming first has to convert it into a Spark RDD, which is basically a collection of events batched together, and then that RDD has to be passed into the logic. Your logic is then applied to that RDD. So basically, it's a micro-batch stream processing framework. That is the main difference between these 2. Now that leads to interesting trade-offs. When would you use Spark Streaming versus when would you use Storm? Well, the advantage of using Spark Streaming is that you don't have to keep learning a new API. Same API which you use to develop your program for doing simple transformation kind of remains the same when you also do stream processing. So if you have a bunch of Java or Scala devs who are already comfortable in the core core Spark API, they can easily migrate their app to be a stream processing app with little effort because the API looks very similar. Whereas if you were to then take that same process and implement over Storm, you now have a completely different API, completely different type of data modeling considerations which you have to worry about. So that is one advantage of using Spark over Storm. Now, you would use Storm over Spark streaming when your latency has to be very, very small. So Spark streaming can go down as much as 500 milliseconds. Anything smaller than that, and Spark streaming begins to fail. Storm, for that matter, can go down to extremely small latencies, like on the order of single-digit milliseconds, because it can do true event by event. So these are some of the considerations when you would use Spark versus when you would use Storm. Majority of the cases, Spark streaming is fine, but for certain use cases such as fraud detection, where you want to be able to detect a fraud as soon as a credit card is swiped, and you don't want to wait for 10 credit card swipes to be batched up in order to make a decision, that's some of the cases where Storm is used, for example. Let's look at sizing now. So far we have given a very big overview of the logical components, what they're used, how they're connected. Now let's look at concrete numbers. So you have built up this reference architecture. You want to now go ahead and implement this. How many machines are you going to buy? What are the number of HDF machines? How many nodes would you need for storing the data? How many years of data are you looking to store? So all these considerations will be now addressed in this section. So first, what I will do is I'll explain at just the numbers. How fast can Hortonworks Dataflow operate? How fast can Kafka operate? How fast can Storm operate? What's the recommended sizing for HBase? And then once we are equipped with that knowledge, we will look at how much data is our megacorp trying to ingest. What is the data requirement for megacorp? And then we will combine those two concepts in order to come up at concrete numbers for the machines themselves. Okay, so HDF, which is the Hortonworks Dataflow, it scales out very linearly in a very nice manner. On a single node with just one to two node HDF cluster, with each node having around 8 cores with 6 disks per node, and just not a lot of memory, just 2 gigabytes of memory per node. If you have a machine like that, you can easily do 50 megabytes per second and up to thousands of events per second. So the throughput you're going to get for a single node NiFi machine, which has around 8 cores and 6 disks, you can expect around 50 megabytes per second. Now, if you want to scale that out, if you want to have more than that, you would just add more machines to the NiFi cluster, and you would run the same flow on a different machines. Okay, so then it scales out linearly. So for 100 megabytes per second, you would have 3 to 4 nodes. 200 megabytes per second, you would have 5 to 8 nodes, and it goes from there. Okay, so that is this broad sizing guideline for Hortonworks Dataflow. Kafka, which is the pub-sub messaging bus, which typically connects HDF to Storm. It sits between NiFi and Storm. The sizing for Kafka, just general rule of thumb, is that each Kafka node, the typical recommended hardware for Kafka, as we'll see later, a typical Kafka node can do 10 megabytes per second. In terms of events, what we typically see in typical IoT applications is 100,000 seconds per node. Okay. If you need higher throughput, you need larger batch size. Okay. Kafka also has a notion of partitions. So partitions are basically the scale out for a particular event. So the more the number of partitions, the more it scales out. So you also have a different equation depending on the number of partitions, but that gets a little more complicated, and that's a more fine-grained analysis at a very high level and a very broad level, and that's the rule we'll follow when we come to real sizing, is that one Kafka node can do 10 megabytes per second or 100,000 events per second. Storm very nicely fits with Kafka, actually. Storm's processing speed is also very similar to Kafka. So again, 100,000 events per second per supervisor node, or 10 megabytes per second throughput. You're going to get pretty much the same speed with Kafka and Storm. Again, Kafka and Storm complement each other very well, since Kafka is a very disk-bound operation. So Kafka events are stored inside the disk
of the local machine, and they're persisted for 7 days. Whereas Storm is a very memory and CPU bound process, because it tries to keep the state all in memory. So you can co-locate Kafka and Storm on the same node, and they don't really interfere with each other, but they do consume all of the resources on the same box, so you cannot run any other process on it. So hence, when we talk about HDF relaying info to Kafka and then Kafka relaying info to Storm, keep in mind that Kafka and Storm processes are actually running on the same physical machine and hardware. HBase can easily, again, do 10 megabytes per second of write throughput. And we recommend that, not just recommendation, but it's actually common practice that everything in HBase is compressed. We say that each HBase node can do around 1 to 3 terabytes per node of compressed data. Okay. So now let's look at the problem statement again, before we get down to the numbers of how much cluster size and HDF nodes and Storm and Kafka nodes will Megacorp need. So Megacorp, again, was looking at reducing the number of incidents by a number of X percentage, and then she had asked TAM to come up with a number, and TAM came up with this, right? They said 10% reduction in incidents will move the company from a high risk to a low risk insurance category, right? So what this means is that TAM and Ms. Brady are actually looking at not just point-in-time solution, not just for the next few months. They're actually revamping their whole architecture, and they're going to store and use this data and this infrastructure for the next 5 years. So what we are sizing for is 5 years data volume. Okay, so the 5 years data volume is the number we have to account for. Okay, now how much data? So we are storing 5 years of data, but what is in a cluster? Let's say I have 1 petabyte of data which I'm trying to store. How big should be my cluster? Okay, so you would think that 1 petabyte means that you have to make a cluster which can store 1 petabyte of data. Exactly 1 petabyte? That's not really the answer. The problem happens that when you store data in HDP, in Hadoop, in HDFS, what happens is when you analyze the data set, the processes themselves generate some intermediate files. So when a MapReduce process or a Hive process or Spark process is running on top of the HDFS data set, it's gonna generate some intermediate files, which can easily be very, very, almost up to 30 or 40% of the data set being analyzed. So we have to account for that, first of all. We also have to account for the replication count. So each data block sitting in HDFS is replicated 3 times. Okay? So the replication factor is also a consideration. And also we need a temporary scratch space for all the processes to execute. Okay, this is different from the intermediate size data, which is basically the data generated between the map and reduce portions of the process. The temporary space is just some scratch space for the processes themselves. Okay? So not only do we have to account for our actual 1 petabyte of data, but we also have to account for the intermediate files, the replication count, and temporary space. Okay, so these are the factors which will contribute to the overall expansion of the data we need to account for. But this is offset by the compression ratio. By that, what we mean is anything stored in HDFS, we turn on compression on it. Okay, compression is useful because not only does it save you storage cost, but actually compression sometimes even allows you to process the data in a more elegant manner. The compression formats used in Hadoop, for instance, Avro, they not only compress the data set, but they are also able to split the data into more convenient blocks. And they have sync markers in the head of the data block, which allows applications to understand where to fetch the next block from. So compressing the data is always a great idea. And the compression sizes we typically see are of the factor of 3. So in this equation, which will give us the final data set size needed, in this equation, we typically see that replication count and compression ratio cancel out with each other. Because the replication count is 3, compression ratio is almost 3, these cancel out with each other. And all we need to do is then account for intermediate size and temporary space. Okay. So the temporary space is usually 1.2 to 1.3. And if you multiply the intermediate size by temporary space, you come up to a number of roughly around 1.5. So So that becomes your broad guideline. Let's say you're trying to store X bytes of data, you would need X times 1.5 bytes storage capacity on your cluster. Okay? That is the total, that's how we size typical Hadoop clusters for IoT apps. How does that boil down to Megacorp? In Megacorp, we have 5,000 trucks. Let's assume that each truck is generating 10 events per second, and the size of each event is 128 bytes. Okay, so how much data do we need for 1 year? Well, in 1 year, we're looking at 5,000 times 10 times 128 times the number of seconds, which becomes 160 times 60 times 24 times 365. So we're looking at 1 year raw sensor data storage itself is 200 terabytes. I multiply that by 5 years because we are trying to do capacity planning for 5 years here. It becomes 200 terabytes times 5, which is 1 petabyte. But then we multiply that by 1.5, which is what I explained in the slide earlier. So we have 1 petabyte times 1.5, so that becomes 1.5 petabyte. So this is our total data which we should be storing. This is our estimate. We will need to have a cluster as large as be able to store 1.5 petabytes of data for the next 5 years. That is our target. The question now is, how many nodes do we need to store 1.5 petabytes of data? Just the raw sensor data which is coming in, how many nodes of actual physical boxes do we need? So the answer will be shown in a couple slides later. Now let's look at the other storage aspects. For H-based Kafka, Storm, and NiFi, what are the storage requirements? So let's look at first the stream processing or the fast-moving aspect of data here. So for Kafka, Storm, and NiFi, the ingest rate we are targeting at is what? So we have 5,000 trucks, each generating 10 events per second, and each event is 128 bytes. So we get an ingest rate of 6.4 kilobytes per second. This is our ingest rate. So the question is, for 6.4 kilobytes per second ingest rate, how many of these nodes would you need? So again, my pedagogy here is that I'm giving out these calculations, I'm posing some questions, and I'll answer them in a slide later. Okay. Again, we have made a decision that we will store last 15 days of data in HBase. Okay. So anything which is being generated by the Storm processor, the predictive analytics arrived at by Storm processor, we will store those insights into HBase for 15 days. So basically, we have to size HBase for the last 15 days of data in the worst case, because we are assuming that for each event coming in, we are doing something to it, and we are storing a value associated with that event. So how much HBase storage do we need for 15 days? So again, it comes down to 10 events per second times the number of seconds for 5,000 trucks for 15 days. So that becomes 8.2 terabytes. So the question now is, how many HBase nodes do we need? So we have three broad categories of node calculations now. We need one category of nodes which are just going to store the data for 5 years, which is what? 1.5 petabytes. Then we have another broad category of nodes which are doing data ingest and processing, real-time processing, which is Kafka, Storm, and NiFi. So our target over there is that we need as many nodes as we can, which can handle 6.4 kilobytes per second ingest rate. And then we have HBase sizing requirements, which are predicated on 8.2 terabyte data storage. Okay? So now comes the answers. Now, just for the storage of 1.5 petabytes of data, we have to, the way we arrive at the number of just storage or worker nodes is we would take 1.5 petabytes and divide that by storage per server. Now, the storage per server in HDP clusters is typically 48 terabytes. One physical box can typically store 48 terabytes of data. So the number of nodes hence becomes 1.5 petabytes divided by 48 terabytes, that becomes 32. Okay? So we now need 32 physical boxes, each with a 48 terabyte storage density in order to save 1.5 petabytes for 5 years. So this is our number, just for data storage of raw sensor events. How about NiFi, Kafka, Storm, HBase? Now, if you recall in our earlier slides, I said that NiFi can collect 50 megabytes per second per node. Kafka can ingest 10 megabytes per second per node. Storm can process 100,000 events per second per node, basically the same as Kafka. And each region server can store 1 terabyte. That's our broad guideline. Okay. So for 6.4 kilobytes per second ingest rate, we just basically need only one NiFi, one Kafka, and one Storm node. One NiFi is sufficient for ingesting 6.4 kilobytes per second. It can do all the way to 50 megabytes per second, so one NiFi node is more than enough. Similarly, one Kafka and one Storm nodes are sufficient. However, for HA purposes, we will use two NiFi nodes and we will use three Kafka nodes, just to be on the safer side. For high availability, although just one node is sufficient, but we will use multiplicity of nodes in order to do HA. The number of H-based nodes needed is basically 8 because we have 1 terabyte per H-based region server, and we needed how much? 8.2 terabytes of H-based storage. So the amount of H-based storage needed here is also 8 nodes. Also, we will co-locate Kafka and Storm. So 3 Kafka nodes and 1 Storm node, but we will have 3 Kafka and 3 Storm nodes co-located, like I said earlier, because they complement each other. One is a disk-bound process, Kafka, and Storm is a memory and CPU-bound process, so we can co-locate them. And we will also co-locate data node and HBase. So HBase can easily sit on each data node or worker node. So hence, what we get is we need 8 HBase nodes, but those 8 HBase nodes will be consumed by those 32 worker nodes over here. So we have total number of HBase and data nodes or worker node needed is 32. So out of these 32, 8 will be both data node and HBase, and the rest 24 will be just data nodes. NiFi, we need 2 nodes because of HA. Kafka and Storm, we will have 3 nodes just for HA purposes. And then we have some other nodes which are responsible for the management of the cluster. So we will have 5 master nodes which are going to manage the whole cluster. And then we will also have 2 client nodes which will allow people to log in to the cluster and run their jobs. Okay, so the total number of nodes then becomes 32 plus 2 plus 3 plus 2 plus 5 becomes 44. So this is the total number of machines we need to purchase in order to realize a solution for Megacorp for a data ingest rate of 6.4 kilobytes per second for 5,000 trucks and for storing 1.5 petabytes of data for 5 years. How does this pan out into an actual physical architecture? It looks like this. So on the right side, we will show Megacorp's data center. And on the left side are all the trucks which are generating these events. Okay? So I have truck 1, 2, 3, all the way to truck 5,000. They are generating events one by one. They are now flowing into Hortonworks data flow. So now they have arrived at the data center. We have 2 NiFi nodes which are collecting these data. Actually, just one NiFi node is collecting all the data. The other one is just a backup. It's doing redundant storage. Now, once NiFi collects these events, NiFi then pushes them out to the Storm and Kafka nodes. So now we have 3 Storm and Kafka nodes. Again, we could have just used 1, but we are using 3 for HA reasons. So this forks out into all these 3. Then the Storm and Kafka nodes then operate and do their number crunching, and then they store the data back into HBase or just HDFS. Kafka is pushing out both to Storm, and one Kafka stream is going into data nodes. And we said that we needed what? 8 HBase nodes. So out of those 32 total worker nodes, we have 8 HBase nodes, and the rest are just rest 24 from data node number 9 to data node number 32 are just worker nodes which are just storing raw events. So we get, just for the data flow perspective, all the information coming into NiFi, going into Storm and Kafka, and then 8 HBase nodes, plus total 32 worker nodes, with 8 HBase and data or worker nodes co-located with each other. And then we have around 5 master nodes for the management and operation of the cluster. And then some 2 client nodes. We call client nodes edge nodes because these are located outside of the secure zone. So they have public-facing IP addresses, these 2 nodes. So users can log into these machines and run their own jobs. Okay? These 5 master nodes are running master processes like name node, main Ambari management node, and so forth. Okay? So this is it's sort of a mid-level diagram of how you would visualize this cluster. At a more fine-grained level, when I say 5 master nodes and 3 ingest nodes and 2 edge nodes and 32 worker nodes, what do I mean by that? What are some of the processes which are running on these each boxes? So this is a typical HTTP service layout diagram. This is not showing Hortonworks data flow. This is showing this box, this HTTP box here, the edge nodes and the Storm Kafka nodes and the worker nodes. We're trying to expand on that on this piece over here. So service layout looks like the following. In these 5 master nodes, we're going to split all our management services. For instance, we'll have name node 1 on master node 1 and name node 2, which is the second, which is the backup name node for HA on master node 3. Similarly, we'll have resource manager, which is the orchestrator for all the yarn processes running on the system. Resource manager will be present on a master node 2 and also on master node 3. Okay. So as you can see, these 5 master nodes will have all the master and management services split equally between them. Okay. The ingest nodes, which are basically taking the data out of NiFi, are going to run Kafka and Storm only. No other processes running on them. Then the edge nodes. So Nox and clients are going to be sitting on the edge nodes. So clients, as you know, are just a way for users to interact with HTTP. And Nox is, again, a gateway and a perimeter security solution. So users can also use Nox in order to load balance their requests going into HTTP cluster. Okay. Worker nodes are worker node 1 through worker node 32, out of which there will be 8 worker nodes, which will have both node manager and HBase region server, and the rest of them will just run data nodes. Let's look at now the physical machines which we typically recommend users to buy for such types of nodes. So master node specs are usually, we require 12 plus total cores. Dual socket CPUs are the best. 128 to 256 gigabyte RAM is more than enough for a master node. Basically, we need around 2 1 terabyte drives. Master nodes are not very heavy in terms of their hardware requirements. They're kind of mid-sized commodity servers because they are not really doing bulk of the processing in any Hadoop cluster. The approximate cost of a master node is going to be around $8,000 to $18,000. The NiFi node specs are similar to the master node specs with one crucial difference. We don't require as much RAM as the master nodes. So we just need 8 cores with 16 gigs of RAM, and the approximate cost per node for a NiFi node is around $5,000 to $8,000. Yeah. Slave nodes. So these are the workhorses of any Hadoop cluster. These are the guys who are running all the data nodes and the actual processes. These tend to be a little more heavy duty. We require 12 plus cores, 32 to 64 gigabyte RAM, can go all the way to 128 to 256 gig RAM, depending on your use cases. Of course, you would use higher memory spec boxes if you're going to run, for instance, Spark. Okay. The main difference between the slave and master nodes is not just in terms of the memory requirement, but also in terms of disks. So slave nodes have a higher number of disks attached to them because they are used not only for data storage, but also processing. So if you have a balanced cluster, we say that you can use 12 times 2, which is equal to 24 terabytes of storage space per box. So you would hook up 12 2 terabyte SATA drives. That will give you a balanced cluster. If you want to use the worker nodes primarily for archival purposes for HDFS data, you would use 4 terabyte disk drives. And if you're just interested in processing and you're not worried so much about storage, you can go down in the number of disks you have to just 1 terabyte per disk, so you would get around 12 terabyte storage density. The approximate cost per node for slave is around $5,000 to $12,000. All right, so we have seen now how to size our cluster, what's the reference architecture. We are all set with the purchase order, but first let's look at how are we going to assemble a team of people in order to realize this project. Okay? So project plan looks like this. So Tam puts together, the consultant puts together the following project plan. She says that, hey, Ms. Brady, it's going to take us 120 days from scratch in order to build out the solution. Where 10 days will be used for strategy. We just want to understand the problem statement at hand. We'll design a broad, big solution. Then we will send all the employees involved in the construction of the solution of Megacorp to Hortonworks training, right? So Megacorp not only has hired these 4 consultants, but they also have their own developers. But they need to get trained in order to understand how to work on the data sets and how to use Spark and Storm and so forth. So the training of those people will themselves take 10 days at Hortonworks University. Once they come back, we will start building out the solution and designing and building the solution out. That's going to take around 60 days. Finally, we will do a testing and prove out of the solution, iron out any kinks. And lastly, we will implement the solution, we'll promote it, and we'll put it into production. So 10 plus 10 plus 60, 30, 10 gives you 120 days. So from scratch all the way to the end, it'll take 120 days for this project. And that's a typical number in most IoT apps we see. The resource plan is very simple. There's a project manager, there's a consultant, Jim, and then there's other, Jim is now becomes the engagement manager consultant, who is a new person who has been hired as a consultant just to run the show here, basically. Tam, Varun, Sue, etc., their roles remain the same. Now let's look at the project cost and ROI. With all this team in place, what is the, and with all the team in place and with all the machines we need to buy, what is the cost we are looking at? What's the project implementation cost? So hardware, we saw we needed 44 machines, physical boxes. On an average, we are looking at spending around 10,000 US dollars per machine. So the hardware cost is 440,000 US dollars. Now, 44 hardware boxes, in order to get HTTP subscription support on those boxes, we sell by node count. So 44 boxes turns out to be 11 SKUs. So each SKU for software HTTP subscription is 4 nodes. Hence, 44 nodes is 11 SKUs. And at $18,000 per SKU, we are looking at 198,000 US dollars. Okay. Similarly, for HDF, we got 2 SKUs. Each SKU is just 1 node. And $36,000 per SKU, we get 72,000 US dollars for that. Okay. Now let's look at HR cost. So dev and test consulting, right? So these were the consultants which the company obtained from the SI partners of Hortonworks. So excellent SI partners of Hortonworks are experts at solution build out and design. So these consultants were billed at $300 an hour. And there were 4 resources for 8 hours per day for 95 days. So these were the Tam, Sue, Jeff, and Varun, right? So those 4 people were used for 95 days. And we would say that on an average, they consume $300 an hour. So total, their fees comes down to around 912,000 US dollars. The engagement consulting, that's the role of the engagement manager. We have reduced it to just half of the total project cost. So 360 hours just for one person for 45 days, billed at $300 an hour is 108,000 US dollars. And then we have the whole Megacorp staff, the development staff being trained at Hortonworks University. And that turns out to be admin, analyst, and data science training for 30 associates. That's just one unit cost of $2,500 per person. So multiplied by 30, you get 75,000 US dollars for that. And add to that some travel and other incidental expense of 100,000 US dollars. And there's a rough estimate, if you add up all these numbers, we arrive at 1.885 million US dollars. So all the way from purchasing the hardware to training people and then implementing the solution and buying the HDP and HDF support subscription services, and realizing this from scratch in 120 days is going to cost us 1.885 million US dollars. So that's our cost. Now see if we met our target or not. Did we arrive at the ROI or not? So the project ROI. So insurance cost reduction, if you remember what Tam said, that if you can reduce by 10%, we will save on an average 5 million US dollars per year. And in the very first year, we have spent, what, $1.885 million. So in the first years itself, we have saved $3.1 million. So we have more than broken even. We have more than recovered in the very first year of implementing this project, all our cost. So we have broken in, not just broken in, but we have recaptured all the ROI right in the very first year. So this comes to the end of our presentation. In this presentation so far, we saw everything about IoT applications. We saw how Miss Brady was able to save the insurance premium cost using HDF and HTTP, using a completely modern data architecture. It has been a pleasure to talk to you about IoT applications using HDF and HDP. If you need more info, please go to our website and look at our tutorials and our different Hortonworks University training paths in order to understand more. Thank you.